Let's discuss the vertical circular motion of a pendulum bob. We all know about a simple pendulum. In this, there is a string of length L with a bob of mass M hanging at the bottom of this string. If we throw the bob with an initial speed u in horizontal direction, the bob will start following a vertical circular track like this. And we can see as mg is acting on the bob in downward direction, as bob goes up, we can say at an angle theta, the speed of bob will continuously decrease. In this situation, as it goes up and its speed is continuously decreasing, speed at any position at an angular displacement theta we can obtain by using work energy equation. So if we using work energy equation, we get initial kinetic energy, we can write it is half mu square. As it reaches this point, the height to which it is raised up is say h. This h can be obtained as this total length is L, this is also L. So this length we can write it as L cos theta. So this height h to which the bob is raised up can be written as L minus L cos theta, which is L into 1 minus cos theta. So if it is raised up by a height h, gravity is doing negative work on the bob, so we can write it minus mgh. H we can write as L into 1 minus cos theta is equals to the final kinetic energy of bob at the angular displacement theta, it is half mv square. Now in this situation, this m gets cancelled out and we can get the value of speed of bob at an angular displacement theta, which is root of u square minus 2gl 1 minus cos theta. This is our equation number 1 and a very useful equation for various analysis related to vertical circular motion of this pendulum bob. In this situation, at this angular position theta, we can say it is experiencing its weight mg in downward direction and a tension will be acting on the string toward the center. Along the radial direction, we can say there will be a component of its weight, that is mg cos theta, acting on it. And due to this, we can say the net centripetal force acting on bob can be written as T minus mg cos theta. So in this situation, we can write at this position T minus mg cos theta, which is the net centripetal force acting on it, is mv square by L. If we substitute the value of this speed over here, we'll get T is equals to mg cos theta plus m by L into v square, that is u square minus 2gl into 1 minus cos theta. On simplifying, we'll get T is equals to mu square by L minus 2mg plus 3mg cos theta. This is equation number 2, which is also a very useful relation, which gives us the tension in a string at an angular displacement theta if the bob is thrown from the bottommost position with initial horizontal velocity u. Let us discuss about angular amplitude of a pendulum. Just now we have studied about the motion of a simple pendulum in a vertical circle. So if we just consider a simple pendulum hanging from a fixed point from the ceiling, say it is of length L. If we throw the bob of this simple pendulum with an initial speed u, we know that it will start following a vertical circular path, and we also know that as it goes up, the speed of this pendulum bob continuously decreases. And the equation we have already studied that from equation 1, the speed of pendulum after traversing an angular displacement theta from the vertical position of a string, the speed is given by root of u square minus 2gl 1 minus cos theta. Now as it is going up, we can see that the speed is decreasing. If we throw it with a small speed, it is obvious that it will move up to a particular angle and then finally its speed will become 0 and then it will return. So the maximum angle up to which it will move and then come back, that angle we call angular amplitude of this pendulum. So we say if phi is the angular amplitude, this implies at theta is equals to phi, the final velocity has to become 0. Say the bob will reach this position where the total angle become phi, we can say its final velocity becomes 0 and then because of gravity it will come back. So in this process, by using this equation, we can get the value of phi, like we take v is equals to 0, this is equals to root of u square minus 2gl 1 minus cos phi. If we square it, you can see we are going to get 0 is equals to u square minus 2gl plus 2gl cos phi. From here we can write the value of cos phi, this is equals to 2gl minus u square upon 2gl. This equation itself is important, which says that angular amplitude phi is equals to cos inverse of 2gl minus u square by 2gl. This is quite an important relation which is going to be helpful in many of the cases. Always remember this angle phi is giving us the angular amplitude of oscillation of the pendulum bob, because if it is thrown with a small speed, it will reach up to the position of angular amplitude and then it will return and it will oscillate in the lower half of this circle. So always remember this expression. In continuation, we'll discuss another concept, the calculation of angle where a string of pendulum will slack. We have studied that if the bob of a simple pendulum is thrown with the initial speed u, it goes up and the speed decreases. It is quite obvious that in lower half of circle, when the pendulum is moving, at the bob tension in the string will be acting in inward direction and a component of weight, that is mg cos theta, will act on it in radially outward direction. This we are talking at an angular displacement theta. And we can say the net angular at a position theta, the net centripetal force is provided by T minus mg cos theta. Then obviously the value of T will be more than 0. But it may be possible that if the bob will reach the upper half of circle, then at a position it is possible, one, the component of weight is acting in inward direction as well as tension is also acting in inward direction. If the component of weight in radial direction is more than tension, obviously the tension will become 0 and the string will slack. And say at a particular angular displacement theta, if the tension becomes 0 and the bob is having some speed, it will follow a projectile path and finally it will carry on the free fall motion under gravity only. So we can say this particular angle theta we can calculate by substituting the value of T equal to 0 in our equation 2. Now we can write at theta less than pi by 2, tension in a string will never be 0. And we can say at theta more than pi by 2, it is possible, again it is not necessary, it is possible that at some angle T becomes 0. Now from equation 2 we can write T is equals to mu square by L minus 2mg plus 3mg cos theta. Now let at theta is equals to alpha tension becomes 0. This implies we use 0 is equals to mu square by L minus 2mg plus 3mg cos alpha. In this expression, m gets cancelled out and on solving we'll get the value of cos alpha is equal to this 2gl minus u square upon 3gl. or the value of alpha will get cos inverse of 2gl minus u square by 3gl. This is the expression of the angle at which the string will become slack and the particle will follow a projectile motion under gravity only. So always remember this expression also.